Okay, good morning. Now, I would like to discuss about the noise figure of a cascading network. Noise figure of a cascading network. Okay, what is meant by noise figure and what for this parameter is used? The noise figure we have seen already in many topics of communication. That is, the noise figure is the ratio of input signal to noise ratio to output signal to noise ratio. That is the way you can define the noise figure. But what for this noise figure? Why we have to estimate it? Okay, that is, by knowing the noise figure value, you can see the noise rejection capability of a given network. We can know how far the noise will be rejected by the network. Okay, by knowing the noise figure value, we can estimate up to which level the amount of noise will be rejected by the network. That information we can know by the noise figure. The another parameter which is used to know the same information is noise factor. Of course, both are same. Noise figure and noise factor are both are same. But what is the difference is the noise figure has no unit. The noise factor has the unit called decibels. So noise factor value expressed in terms of decibels. That is, the decibel representation of noise figure is known as noise factor. Both are same. Both are same. Used for to know the rejection capability. Okay, but what it is the decimal representation of noise figure is the noise factor. Okay, and already I said that the ratio is input signal to noise ratio to output signal to noise ratio. Therefore, we can express Fn equal to S in by N in divided by S out divided by N out. Okay. Since the input noise is KTBN, KTBN, KT not BN, therefore by rearranging this ratio, we can say finally Fn equal to N out divided by KT not BG, KT not BG. Okay. So where what is G? What is G is okay by rearranging it we can get the equation actually n out divided by n in into s out divided by s in. S out divided by s in is signal output power divided by signal input power is the gain. That's why this part is G. Whereas n in is KTBN. Okay, so now n in is replaced by KTBN. N out is as it is. Okay, and the different notations represents Sn is available input signal power, Sn is available input signal power, S out is available output signal power, Nin is available input noise power, N out is available output noise power. Okay, G is the gain. G is the gain. Its ratio is S out divided by S in, and KTBN is N in, and here K is the Boltzmann constant, T is the temperature, B is the receiver noise bandwidth. Receiver noise bandwidth. Like that, you can say the different notations what we have in the noise figure. Okay. So from this equation, from this ratio, we can know that the noise figure is the ratio of the total available output noise power to the amplified noise of the network, the amplified noise of the network. Because why it is called amplified noise? Since it is the multiplication of input noise with the gain of the network. That's why it is referred as the amplified noise. But what is the total output available noise power is the available noise power at the output plus the noise introduced by the network itself. The noise introduced by the network itself. Okay, therefore we can express the same is like this. Therefore, Fn equal to the N out is the sum of amplified noise plus the noise introduced by that network divided by amplified noise. Okay, so that's why this Fn is can be written like this, which is equal to 1 plus delta n divided by kt naught b n g. kt naught b n g. Okay. Where delta n is, okay, where what is delta n? That is the noise introduced by that network only. That network only. And this is the amplified noise. This is the amplified noise. Sum of these two represents the total noise available at the output. Okay, and the denominator is amplified noise, so that it comes like 1 plus like this. So from this we can express delta n as kt naught bn g into fn minus 1. Fn minus 1. Okay. Now let us see the noise figure of a cascading network. With reference to cascading network, how can we express the noise figure? Okay. So, but here I am taking a two-stage cascading network. A two-stage cascading network. Two stages now the network consists. Okay. The first stage having the noise figure is f1, gain is g1, but the bandwidth is bn. Okay. F1 is the noise figure value of the first stage, G1 is the gain of the first stage, Bn is the bandwidth of the first network or first stage. Similarly, the second network noise figure is F2, gain is G2 and bandwidth is Bn. Okay, so F2 is the noise figure, G2 is the gain and Bn is the bandwidth. Okay, here if you observe, the bandwidth is same for both the networks. The bandwidth is same for both the networks, whereas the noise figures and gains are the different to one network to another network. Okay, and n naught is the total, that is the available noise output power for the cascading network. For the cascading network, the available output noise power, and the notation f naught is used to express the noise figure for the two-stage cascade network. Okay, so now this type of two-stage cascade network we assume to derive the noise figure of the cascading network. Okay, so now from the previous analysis, the n out, that is available output power, is noise power. Available output noise power we can express as, in terms of noise figure, is f naught g1 g2 kt naught bn. F naught g1 g2 kt naught bn. Okay, this is also equal to the noise from the network at output of network 2, noise from network 1 at output of network 2, plus the noise introduced by the second network only. Okay, the noise from network 1 at output of network 2 plus the noise delta n2, the noise delta n2 introduced by the second network only, by the second network. Okay, so therefore f naught g1 g2 kt naught bn equal to, what is this first term? The first term is kt naught bn f1 g1 g2. This is the noise from network 1 at the output of network 2. Okay, how we can write this directly is, from the previous one, in the first stage case, in the before starting the cascading, in the previous slide you can observe this one, plus the noise introduced by the second network. Okay, that equal to kt naught bn f1 g1 g2. The noise introduced by the second network also from the previous one stage relation we can express as f2 minus 1 kt naught bn g2. f2 minus 1 kt naught bn g2. Okay, so like that the right hand side part we can express. Okay, therefore what is f naught? Therefore f naught equal to this part divides the right hand side part. This part g1 g2 kt naught bn divides the two terms of the right hand side equation. Hence the f naught comes like f1 plus f2 minus 1 divided by g1. So this is the noise figure equation for two-stage cascade network. Suppose if the circuit consists three stages, how can we express it? F1 plus F2 minus 1 divided by G1 plus F3 minus 1 divided by G1 G2. Okay. Similarly for four stages, the next term is F3 minus 1 divided by G1 G2 G3. Okay. Similarly for the n stage cascade case, for the n stage cascading case, the expression we can express as F0 equal to F1 plus F2 minus 1 divided by G1 plus F3 minus 1 divided by G1 G2 plus dash 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 Fn minus 1 divided by G1 G2 G dash 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 Gn minus 1. Following, this is the noise figure for the cascading network of n stages, consisting n stages. Okay, next coming to noise temperature. Noise temperature, we can express it as TE, effective noise temperature. Okay, so what it is effective noise temperature? This is the temperature at the input of the network which would account for the noise delta n at the output. Okay, therefore the delta n we can express in terms of effective noise temperature as KTE BNG. KTE BNG. Okay, using this expression, if you substitute in the noise figure Fn equal to, already we know it as 1 plus delta n divided by KT naught Bn. Okay, of course G. Okay, now the delta n if you substitute in with TE notation, therefore it comes like Fn equal to 1 plus TE divided by T naught. Hence TE equal to Fn minus 1 into T naught. Therefore TE equal to Fn minus 1 into T naught. This is for one stage. Whereas for multi-stage network or the network consisting n stages, the noise temperature we can express as T equal to T1 plus T2 by G1 plus T3 by G1 G2 plus T4 divided by G1 G2 G3, like that. Okay, so these are the expressions for noise figure and effective noise temperature for the n stage multi-stage network or cascading networks simply, right?